Okay, starting. It's uploading the okay, keys is on the list. Okay, so keys is coming.
Yes.
And just making a host. So keys, you co-host already.
It's
And
connecting.
yes. Okay, and at this moment we already connect to the YouTube channel. So we are already on YouTube channel. Keys is connecting, and if you don't mind, okay, let's wait a couple of minutes to see if Keys comes, and then I start recording the talk. Okay. Hi, Keys.
Hello, how are you?
Hello, hello.
It's nice to see you again.
Everything.
Hi, Keys.
Hi, Maria.
Hi.
So, Keys, everything is okay. We start already the transmission. We are already on YouTube. And
okay.
I will start right now the recording, or I will welcome everyone and then start the recording, okay?
Okay, we have 2 minutes more before the official starting time. So I will start on time. So Maria, it's about 40 minutes or so. We'll make a sign, 45.
It's 30 minutes plus 10, no?
Yeah, and then I'll make a sign for questions. So we overran on the plenary, but the next session starts at 5. It's great to see you face to face at last.
At last. No, there were a problem on communication. I don't know why, but okay. Now it's resolved.
Maybe my mails went into the spam box or something. You know?
Yeah.
Okay, so I will welcome everyone, if you don't mind. So people is coming, and when you send me keys, I will start recording. We are already online on YouTube. So please.
Yep, I'm ready.
Okay. So, okay, everything is ready, and you can start when you want, please.
Okay, just 1 more minute, let people in. Okay, good afternoon. Welcome to this semi-plenary session at the CMD 2020 GEFES on Thursday, September 3rd. So I am extremely happy to welcome today Maria Grazia Betti, who is a professor at the Dipartimento di Fisica of the La Sapienza University in Rome in Italy.
It's BNB.
Just a few words. So Maria Grazia graduated from the same university back in '85. She did her PhD studies at University degli Studi in Modena, where she continued the first part of her career as a researcher. She became associated professor at Rome La Sapienza 1999, and then became a full professor last year. So her research interests span the realm of nanoscience, as well as surface physics, low-dimensional systems, and functionalization of graphene. And she is well known as a user of synchrotron facilities, ESRF, Soleil, etc., etc., etc. And she also disposes in a lab of facility for electronic spectroscopies on in situ deposited nanomaterials as well as graphene. So today we will listen to Maria Grazia Betti on the tuning of the magnetic response of molecular spin interfaces. And I'm extremely happy to give you the floor. Please.
Thank you very much, Cass. Good afternoon to everybody. First, let me thank the organizer to give me this opportunity to talk about my research on magnetic molecular system, in particular, how to tune the magnetic response of molecular spin interface. First, a brief outline of the talk. So I start to give you an idea of challenges of magnetism in low-dimensional structure. Then I will focus on magnetic molecular system, and I will show you how create ordered magnetic molecular networks against thermal that are stable against the thermal fluctuation. Then I will propose to you a model system of spin interfaces. This is a system where you have molecules, magnetic molecules, not in direct contact with the ferromagnetic substrate, but with a graphene spacer. Then I will try to show you how can we tune the magnetic response of these spin interfaces, changing the molecule, the substrate, or injecting electrons in the system. So, starting from the interest of to reduce dimension and to understand the magnetism in low-dimensional structure, we can start from three-dimensional system, and then we can go from bulk to a multi-layer to a single layer in a vertical confinement. What we will see that we will have a higher magnetic moments and higher magnetic anisotropy energy. This is important to have higher magnetic anisotropy energy because it's higher to the energy of a spin flip. So if you want a stable magnetic structure, a stable magnetic system, you need a high magnetic anisotropy energy, so high energy for a spin flip to be stable. Then there are two added values. Then there is also lower critical Curie temperature if you reduce the size. So the first two are positive. The third one is negative because at room temperature, maybe you can destroy your magnetic state. So there is a lot of research in the last, I can say, 40 years on this system, and this on the right is a very nice Stern-Gerlach experiment to demonstrate that if you have higher magnetic moment if you decrease the cluster size. Then there were a lot of experiments to demonstrate that if you will increase the Curie temperature, if you increase the number of layers, for example. And then if you look at the important the magnetic anisotropy energy, we can see that if you have a single atom, we will have an isotropic system. If we put this atom on a surface, you will increase the magnetic anisotropy energy. This is an example of this example is of cobalt on a surface. And then if you put a cluster, you will have another increase of anisotropy energy. And then you can compare the cluster with the bulk. So in a bulk of cobalt, you have is not isotropic, you have an easy magnetization axis, so a direction, preferential direction for magnetization. Okay, so now if you want to, we were talking about the vertical confinement. If you want to confine the lateral confinement of our system, we can start from the bulk. We can have a dot of a micron scale and then go reduce, decrease the size, and then we can have a nanometer clusters, and then we can arrive to the ultimate confinement. So to store 1 bit of information in a single atom of molecule. So the final goal is to have bistable magnetic states of a single atom or a molecule to represent the ultimate realization of a digital memory. So there were a lot of work to study atoms, not only atoms, also single metal atom in an organic matrix deposited on surfaces. And then the coupling, they were studying the coupling of these single molecular magnets with the ferromagnetic substrate. There is a lot of work, but there are constraints that we have to take into account. So let me start, and then I will show you how can we realize a spin network putting together singular borator atoms on bits. And then the question is, can we realize a spin network stable at room temperature? So let me show you a very interesting paper published 4 years ago, I think, 4 years ago, when they studied the magnetic remnants of a single atom deposited on a surface. This osmium deposited on a surface of magnesium oxide. And then you will see, you will have disordered atoms on the surface. And then they measure the hysteresis. And then there is a remanence, but the remanence is only at 6.5 Kelvin. So at very low temperature. Then there was a very interesting experiment, another experiment a few years later on the same system. They put, with a scanning tunneling microscope, a magnetic tip on top of the atoms. And they were able to reverse the magnetic response. So this spin down becomes spin up because the tip is approaching, the magnetic tip is approaching, and then so on. If the temperature is very low, this is possible. But if you increase the temperature, if you at 45 Kelvin, you see that the magnetization reverses spontaneously. And then the osmium atoms start to migrate if you increase at 50 Kelvin. So it's not possible to freeze this configuration, the spin configuration on the surface. So the remanence is only at 6.5 Kelvin, and the atomic diffusion destroys your magnetic states. So another possibility is to think about molecules, because with the molecules, you can freeze the molecule on the surface if it is interacting with the surface, and then you can study the magnetic response of the atoms embedded in this organic cage. So the organic cage we expect is inert from the magnetic point of view. And then when we study the hysteresis in this configuration, but also in this configuration, this phthalocyanine on the same surface, also in this configuration, we see then the hysteresis, the demagnetization exists at very low temperature, but if we increase the temperature at 10 Kelvin, the hysteresis loop is fully closed and there is no anymore magnetic energy. Then they try to put the same molecule on a ferromagnetic substrate. And this was positive because in this configuration, we have a remanence at higher temperature, but only up. We can have a remanence at 100 Kelvin, not at room temperature. So there was another study. And in this study, they used iron phthalocyanine. Iron phthalocyanine is interesting because it has a very high magnetic moment comparable to a single iron atom. And then it's easy to make ordered spin network with this phthalocyanine because the molecule-molecule interaction allow this very nice ordered configuration. So also in this case, they try to measure the hysteresis, but it was very good, successful hysteresis at room temperature with a magnetization that is non-negligible, but there was, however, there was a big reduction, almost a quenching of the magnetic state. So it was very difficult to measure this for this reason. There was a big reduction in the magnetic moment of the molecule. So we were thinking to propose a system of spin interface where we can preserve the magnetic moment of the molecule, and then we can couple this magnetic moment with a ferromagnetic substrate. And we propose a model like this. So we need ordered spin networks with small independent units. These molecules are for us this iron phthalocyanine with a high magnetic moment. So we organize this on a surface in this way because we have to preserve the magnetic states, and we would like to have a magnetic state that is stable against thermal fluctuation even at room temperature. So we identify this template. This template is constituted by a subset of iridium where we put graphene on, and then we intercalate cobalt. We would like to exploit the decoupling of graphene as a spacer, under the cobalt and the molecule that we put on. So now the question is, can we ensure a magnetic coupling between the molecule and the cobalt are enough close to be magnetic sensitive to each other? And I would like to show you our results. Then I will show you very, very briefly how, because it's not so easy, because it's a model system of spin interface, but it's not so easy to build up. Then we make graphene. It's easy to make graphene on iridium. You will have a corrugated layer of graphene with a moire superstructure, and you can see on the left and in the direct space, sorry, an STM image, in the reciprocal space, a lead image of this corrugation. Then we put cobalt on, and with annealing at 600 degrees, we will intercalate cobalt underneath. So the temperature is important because if the temperature is lower, you will have a cluster of cobalt on graphene. If you have a higher temperature, you will have an intermixing of cobalt with iridium. So if you succeed to build up this architecture, then we checked, we checked the configuration. No, there is no, okay, sorry. The configuration of this system, and then the idea, the first step is to characterize the magnetic activity of the system. So we use X-ray magnetic circular dichroism. This technique is very powerful because if the sample is exposed to an external magnetic field and probed with right on left circularly polarized light, we can have an absorption spectrum. This is the absorption spectrum of cobalt, this L3, L2 edges. So from the 2p states, we are going to the empty states. And the absorption are different if there is a spin unbalance. So if you change from right to left light, polarized light, or if you change the direction of the magnetic field, you will have two different absorption spectra, and the difference between two different absorption spectra is our dichroic signal. This dichroic signal is related by means of the sum rules to the orbital and the spin moment of our system. So this is important because we have a system that is a surface sensitive and element resolved magnetic probe. So we can distinguish the response of cobalt or the response of the magnetic molecule on top. Okay, first, let me show you the magnetic activity of the cobalt intercalated layer. You see on the left, there is the absorption spectra. This is the dichroism. The difference between the panel, the upper and the low panel is the direction of the photon incoming. This is a normal incidence, this is grazing incidence. So in this configuration, we will have the magnetic field in this direction. And so we have this dichroic signal. If we change, we have a dichroic signal with a lower intensity. If you now look at the hysteresis, we will see that the hysteresis we have with a normal incidence as a magnet, as a saturation that is higher with respect to the saturation we have with the grazing incidence. What does it mean? Then the cobalt, in the magnetic state of the cobalt, we have a perpendicular magnetic anisotropy. This is interesting because it's different from the bulk, where it's not perpendicular, well, is parallel to this plane. So in this configuration, we have an easy magnetization axis, and this easy magnetization axis is perpendicular to the molecule. Then we go on, and then we try to understand how it's changing if we intercalate more cobalt layers. So the system we started is a system where a single layer of cobalt intercalated under the rippled graphene, and this cobalt intercalated is commensurated with iridium. This is the lead pattern, is the dichroic signal, and this dichroic signal demonstrated is the magnetism, the magnetic anisotropy, the easy magnetization axis is perpendicular. Then on the other side, we will have 6 monolayer of cobalt. In this case, the system release, and then the cobalt layers are almost commensurate with graphene. So you don't see the moire superstructure. The system is commensurate with graphene, and the dichroism change because it's more intense in the other direction. So in this case, the magnetic states, no, in this case, we will have the easy magnetization axis parallel to the surface. So with this, we switch, increasing in the number of layers, we switch the easy magnetization axis. Now, we have 3 different molecular bits, 3 different molecules that we can put on the system. These are iron phtalosanine, copper phtalosanine, and manganese phtalosanine. They have a common organic cage constituted by carbon and nitrogen. And then in the middle, a different transition metal with different magnetic moment, a different spin. The first case is spin is 1. It depends on the occupation of your orbitals. Also, they have different easy magnetization direction and magnetic anisotropy energy. Now we would like to understand if they can couple with the substrate and how they can couple. So we made the same experiment, an XMCD experiment, now looking at the absorption at the iron sites. So the iron phtalosanine, this is the absorption of iron, and this is the dichroic signal. The dichroic signal is different with respect to the cobalt one. The cobalt one has a positive and negative. These are both positive. If we calculate the magnetization, we will see the hysteresis loop, and this hysteresis loop show a strong antiferromagnetic coupling that is very stable and not broken up to 6 Tesla of magnetic field. So this is the configuration. Then we change the transition metal core. So we put copper instead of iron. In this case, the dichroism has a different sign, see here. And then in this case, you will have a ferromagnetic coupling. So if you calculate the hysteresis, you have the same direction of the easy magnetization axis of copper and cobalt, and the alignment is the same, so it's ferromagnetic. So this is interesting, but then there is the same empirical rule. If you look at the orbital, they are carrying the spin. In this case, the orbital that are carrying the spin for iron phtalosanine are perpendicular to the molecular plane. In the other case, this is parallel to the molecular plane. So in the first case is antiferromagnetic, the second case is ferromagnetic. But if you want to understand why, we can try to understand if there are different reasons. You can have a coupling because these are direct exchange with cobalt. So in this case, you require an overlap between wave function. In this case, the distance is, they are very far. They are more than 5 angstrom far. So in these 2 configurations, these are calculated, but we made also an experiment, X-ray standing wave. It's not possible to have an overlap between this wave function. Then we can have a direct exchange because mediated by graphene. But this direct exchange with graphene also is not possible because the calculation says that the magnetic moment associated with graphene is very, very low. Then another possibility is dipolar interaction, and even in this case, if we calculate this dipolar interaction, it's not possible. So the only possibility, or the another possibility, another hypothesis, and then we can have a super exchange interaction. This is an interaction that was proposed by Mott for transition metal oxide or for other system like this. And then we try with the density functional calculation of the spin density of this system and try to understand if this hypothesis is a good hypothesis. These are spin charge density plot computed with the DFT. So you can see the green is the spin up. The red is the spin down. This is cobalt, this is graphene, this is the molecule. So now you have a green spin up here and red spin down here. This antiferromagnetic coupling. On the other case, you will have green here. This is the same direction. So you have a ferromagnetic coupling. And so in this configuration, you will see that also the graphene is involved. But it's involved, let me try to show you how. In the first case for iron phthalocyanine, when the molecular magnet is carried by out-of-plane molecular orbitals, you will have, from the point of view of the super exchange interaction, a 180-degree antiferromagnetic alignment. These are the orbitals of the molecule, and then they couple with graphene. The graphene is mediate the interaction with cobalt. When you have on the other side copper, you will have in plane molecular orbitals, so these are in plane. Then you have the sigma pi orbital or graphene, and there is a 90-degree super exchange ferromagnetic alignment with cobalt. So then we can study the third molecule, the manganese. The manganese is more complicated. As you can see, the orbitals these are out of plane, these are in plane. But the outer plane dominate. Also in this case, you will have an antiferromagnetic coupling. So this is interesting that you change the atom in the middle and you can switch from antiferromagnetic to ferromagnetic coupling. Now, the most important question is this system stable against thermal fluctuation? So we make the same experiment. In this experiment, we try to change the temperature up to room temperature for all the system, and then we calculate also the exchange energy. You see, for the ferromagnetic coupling, the exchange energy is very low. In the system at 50 Kelvin, the magnetic state is completely destroyed. But for the antiferromagnetic coupling, for all these other system, you will see that the iron phthalocyanine, you will have an exchange energy that is higher with respect to the ferromagnetic one, but is lower with respect to the magnetic one, the manganese, sorry. And then the best one, the best configuration, when you really can have a good, non-negligible exchange energy at room temperature with the magnetic moment, then can resist and stay at room temperature, is for manganese. In this configuration, why this is the most stable configuration? Because in this configuration, you have high magnetic moment on manganese, and then the spin state, the easy magnetization axis on manganese for one monolayer is aligned to the easy magnetization axis of cobalt. So the maximum coupling you will have when the easy magnetization axes are aligned. It is an antiferromagnetic coupling, no? But with the easy magnetization axis aligned. Then, so this is a good result because we can say that we have really a ferromagnetic response at room temperature. Now I will propose to you a way to tune this magnetic state, not only changing the molecule, but changing maybe the substrate. And then we try to find another substrate, a substrate with a higher magnetic moment. So we know the highest magnetic moment among three-dimensional alloys is the magnetic moment of iron cobalt alloy, where the magnetic moment increase from 2.3 of cobalt to 2.7. In this case, I don't want to give you all the details. It was really complicated to intercalate both at the same time. Iron and cobalt was an half of the PhD thesis spent to realize this spin interface. But in this case, we realize a spin interface with a single layer of iron cobalt intercalated, a few layers. Then we repeat the XMCD experiment as I showed you before. And that is the experiment looking at iron and cobalt absorption. And then also in this case, if you have a single layer, you will have a normal incidence, a higher contribution, and the grazing incidence, a lower contribution, as we saw for cobalt. So the out of plane, the easy magnetization axis will be out of plane. And we increase the thickness, and then we have a switch, and also in this case, the diagram is very, very low here, but if you switch the magnetic field, you will have a dichromism very intense, and so the easy magnetization axis will be in plane. So it's interesting because now we can say, okay, I'm not sure that really we will have iron and cobalt intercalated in a way to make an alloy like this, but we can have a cluster of iron and cluster on cobalt maybe, but we made a lot of measurements with the level photo emission and other technique to understand better the intercalation process. In the end, I think one important result and a confirmation to the fact that we are really intercalating an iron and cobalt alloy, almost 50% iron, 50% cobalt, is if you look at the hysteresis loop, they are really for iron is the red one and the cobalt is the blue one, are almost identical. So then using the selection rule and the sum rules, we obtained the orbital moment and the spin moment of the system, and then calculating the magnetization, the total magnetization, you can see then we have a very important increase of the total magnetization in this system. Then the idea is, let's try to couple the molecule with this other substrate. And then this is the experiment where, as a function of temperature, I show you the total magnetization normalized with respect to the response when we have only cobalt. So this is with the alloy iron cobalt, and this is only cobalt. In this case, you will have even a higher magnetic saturation of magnetization at room temperature. So this is a very good results. And then also the exchange energy increased up to 10 millielectron volt. It is a good value for a molecule, no? Now, another idea is how to tune the magnetic response of the spin interface, changing the configuration from ferromagnetic to antiferromagnetic without changing the molecule. An idea is to inject electrons, and this can be done with an alkali doping. Let me show you how. In this case, if you remember, this is the configuration, the area of phthalocyanine. And then in this configuration, we know the coupling is antiferromagnetic. Then we put potassium on. And then if you put potassium, you just start to fill your orbitals, the first one, the second one, and then, so this is a rough representation of the system, but okay. And then in this configuration, the system is non-magnetic. Then if you put another electron, okay, this electron will go in an orbital. This is a planar orbital. So we expect a switch of the coupling from antiferromagnetic, to ferromagnetic one. let me show you the experiment. So this is the potassium doping. We start from the absorption and the dichroism of the clean surface. Then we will start to put potassium on, and there is a clear quenching of the dichroic signal, and then a zero signal here. But now here, you see, we'll start an opposite signal coming out, and then in this configuration, you will have a different coupling. So you start with an antiferromagnetic coupling with cobalt and iron that is anti-parallel, then we'll quench completely the magnetism of the system, and then there is a switching to an from the anti-parallel to a parallel. When you fill the molecular orbitals, there are the in-plane orbitals. So we make this experiment also with other molecules. In this case is manganese, and then also in this case was really interesting also because in this case we observed the switching, but we were also able to measure an hysteresis loop. So I can summarize these results. And we realized the spin interface with independent molecular bits changing the molecule. So we obtain ordered molecular networks on cobalt intercalate graphene. This graphene buffer layer is important to preserve the magnetic state of the molecule. So we have an interaction. This is not a direct interaction, a direct exchange in interaction, but is a super exchange interaction because it's mediated by graphene. Even as the distance from the molecule and the cobalt layer is more than 5 angstroms, there is a coupling. Then we can tune the magnetic states. We can tune the magnetic states of the substrate, changing the substrate, changing and switching the magnetization axis of the substrate. But also we can switch the magnetic coupling, changing the transition metal central atom or injecting electrons. So, but what is most important, all these configurations are stable, almost all, because the ferromagnetic coupling, no, but all the antiferromagnetic coupled configuration are stable even at room temperature. So, I would like to thank, because this work is a common effort with a lot of actors from my lab in Roma La Sapienza, and then with the collaboration with different synchrotron radiation lab, Alba, Diamond, Trieste, SRF, and also with a very important contribution from the theory to make all this calculation from Andrea Ferretti, Daniele Varsano, and Claudia Cardoso from Modena. Thank you very much for your attention.
Thank you very, very much. I can give you a hand.
Thank you.
Thank you very much. It's a lovely talk, very nice talk. I really enjoyed it. So there are some questions. I see a first question from Fernando Bartolome. Perhaps we can unmute him, and you can ask the question yourself.
Can you hear me?
Yes, I can hear you.
Okay, thank you very much for the nice talk. First,
thank you.
Second, I think you have shown the manganese PC XMCD on top of a magnetic alloy, but
yes.
Have you measured the iron PC one?
I didn't measure the iron PC1 because I have iron and iron, so it was intercalated with iron and cobalt. So it was difficult to discriminate in this case the contribution from the molecular contribution from the intercalated layer. Only for this reason, because sure, manganese is more complicated. Is also more complicated to understand.
Would be difficult, but on top of cobalt, it would be in principle possible.
Yes.
Be, interesting to see if the anisotropy of the film does influence the anisotropy of the molecule itself.
Yes, this is important to understand. Yes, we are working on it.
Okay, thank you very much.
Thank you so much. So next we have a question from Andrea Sorrentino. I will ask you to unmute.
Can you hear me?
Absolutely.
Yes.
Go ahead.
Okay. Thanks for the nice talk. Yeah, I have a question. How do you control the potassium deposition on cobalt surface? And so how do you check the electron in the surface?
Yes, this is not so easy because we make a lot of experiments in lab, also with synchrotron radiation to study the core levels and the absorption. So comparing the core levels and the absorption, next step study at the K edge of potassium and then the absorption and the core levels, we can understand how many potassium atoms are going on the surface. And then comparing this with XMCD, and then with the switching of the magnetic states, we can confirm. And also we were measuring also the work function of the system to understand and to have a different calibration of the number of potassium atoms on the surface. So this is an important question. So it's not so easy. Okay. So you have to compare with the XMCD, you cannot.
You don't use also some STM or this kind?
No, we didn't use the STM. Also, I don't think I'm not expert, but I don't think it's easy to manage to understand here really how many atoms are going on the molecule.
Okay, thank you.
Thank you. So next we have a question from Jorge Checa. I will give you the floor.
Oh, okay. Do you hear me?
Absolutely. Go ahead.
Okay. So my question is regarding the coupling. So, well, first of all, thank you for this very clear talk. I really enjoy it. Now, my question is regarding the graphene, because you have like a moire. So I guess that it is really important, the distance that you have between the molecule and the let's say the cobalt layer that you have, in the sense that you probably see fluctuations on the magnetism if you keep increasing the coverage, or in other words, if your molecules start to occupy the upper parts of the moire, do you see changes on the magnetism?
Okay, so this is another important question. So we were monitoring the absorption of the molecules, and it's clear that at the beginning the molecules go in the valleys of the moire.
That's
so you
clear,
have a
yes.
valley and hills. So at the beginning we'll go in the valleys. So when they are in the valleys, there is a very good coupling with the ferromagnetic substrate. Then if you increase the number of molecules, you will see that there are no differences, so the coupling is lower. Because if you intercalate, this is important, if you put graphene on iridium, the corrugation of graphene is very low. But if you intercalate cobalt on iron or iron cobalt alloys, you will have a higher corrugation. So the corrugation will increase. So the distance between the molecule, if it's in the valley or is in the hill, will be very different. So in the valley, you have a distance of more or less 5 angstrom. If you are on the hill, in the case of the intercalation of cobalt, you will arrive to 7 angstrom. And with 7 angstrom, you don't have really a coupling.
Okay, okay.
So there was also an STM experiment of Wiesendanger on this, very, very interesting, Roland Wiesendanger in Hamburg. And they confirmed this.
Okay, thank you so much.
Thank you, Jorge. Are there other questions? Jorge just asked mine. What is the area of your samples, and are you aware or of any influence of possible defects in the graphene, or this is not a worry in this experiment?
In principle, it's very easy to grow graphene on iridium. So we have a sample of 1 centimeter per 1 centimeter. And so the diffraction of the lead pattern is very, very clear. So in principle, also, if you see, we have experiment of carbon 1s core level photo emission, where it's clear, then there, more or less all the surface, the 95% or even more of the surface is with the cobalt intercalated, the graphene doesn't show any clear defects.
Okay, thank you.
Thank you.
Are there other questions for now? I don't see anyone. Are there any hands up? I don't see any either. So I must admit that everything was really perfectly clear. I really enjoyed it. So we're coming on 4:30. We're going to take a group photograph of everybody in the session, as we usually do. So maybe can you stop sharing the screen, then we can all see each other?
Okay.
Yes, and now it works. So Harvey, now you can see the audience, so that's particularly enjoyable. So I will take a few pictures of us also. Here we go. Thank you. Next one. Ah, now there are people with no cameras on, so that's much less interesting. Okay. Okay, what I would suggest, if anybody else makes up his mind and still wants to discuss, maybe you can convince Maria Grazia to stay in the chat a little bit longer. If not, let us thank her very warmly for really this excellent talk. I found it very, very enjoyable, and thank you for accepting our invitation, and thank all of you for assisting and listening to the talk. Thank you.
Thank you.
So the special sessions, the poster sessions of the morning sessions will start at 5. That is in half an hour. Make sure to be there. See you.